Hello, everybody. So today's speaker, I'm very happy to introduce Vijay Varma. Vijay he came here as a graduate student in 2014, I think. Is that right? After working with Ajit in India. And Vijay has done a lot of projects. He's worked on, most of what he's worked on has been involving surrogate models, but he's done other projects in numerical relativity having to do with harmonic initial data and so on. He's had multiple papers that he's published while he's a graduate student. He could leap tall buildings in a single bound. All of this stuff And Vijay just graduated this past May, and now he's a postdoc here for a year. And he's going to tell us about some of his work on surrogate modeling for the final parameters, plus surrogate modeling for the waveform. And so we're very lucky to have Vijay at Caltech still here for another year, and I'm very lucky to have Vijay still at Caltech for another year. But I'd like to, without further ado, bring Vijay up here.
How's that? Okay. Thanks, Mark, for the introduction and also for having me here all the way from the third floor. And so today I'll talk about binary black hole simulations and how we can bring the accuracy of a binary black hole simulation from a supercomputer to your laptop. So before I do that, let's start with some background, although most people would be familiar with a lot of this. So this is a movie that most people would already have seen, but this is a visualization of a binary black hole. And this is based on a full numerical relativity simulation. So you can see the black holes orbit each other and get close to each other until they merge. And then you can see the gravitational waves wobble the space-time around it. I'm not sure if you can see this, but there's two black holes, and then you can see the gravitational waves around them. So one of the main reasons that we do these simulations is to predict the gravitational waves that are emitted in the process. And we want to know that because these gravitational waves, then once they leave the system, they travel across the universe, as we see here, and then they travel across billions of light years until they reach Earth, which should happen any second. And then they vibrate the space-time around us. This, of course, is vastly exaggerated. The real scale is about 1,000 times smaller than the nucleus of a hydrogen atom. So in order to detect that, we, of course, need the most precise instrument ever built, and that's where LIGO comes in. So that's where I'll start. So we have LIGO and Virgo, and we also have planned future detectors. And so the experimentalists are doing this effort of building the most precise instruments, and this is a trailblazing effort that redefines and can possibly tell us new things about astronomy that we never could imagine before. But one of the crucial elements of being able to do this science is to have an accurate model that you can compare with the data that we see in these detectors. In this talk, I'll focus more on binary black holes, which are the most abundant source of gravitational waves, at least so far. So this consists of two black holes, and each of them has a mass and a spin. So the spin is indicated by the spin is indicated by, hold on. Okay, the spin is indicated by the arrow here. However, when you want to model these systems, the total mass scales out in GR, and you can just treat the mass as a single parameter by using the mass ratio, because the total mass in the modeling problem can be put back in after you build the model. So in total, there is 7 parameters that we care about, which is the mass ratio and then a spin for each black hole. So that's a total of 6 spin components. So that's a 7-dimensional problem that we want to solve and be able to predict the gravitational waveform for any given set of black holes and their spins. And in the evolution of a black hole, there's typically 3 different stages that we care about. So when the black holes are far away, they spiral around each other. They do that because they lose energy to gravitational waves, which causes them to get closer and closer. And that happens until they get close enough that they can merge, and the peak is typically associated with the merger. And after the merger, what you have is a highly distorted single black hole. And all of these distortions are then quickly radiated away in what is called the final part or the ring down part of the signal, where the frequency spectrum is entirely dependent on only the mass and spin of the final black hole. So these are the 3 important stages of a binary black hole evolution that we want to model so that we can compare with the data that we see in our detectors. In the early part, when the black holes are far away from each other, of course, we can use analytical methods like post-Newtonian theory to predict the waveform. And similarly, at late times, we can use black hole perturbation theory to predict the waveform using things like quasi-normal mode spectrum of overtones and so on. Okay, so however, in this region in between, where the black holes are very close to each other, the space-time is highly distorted, and the velocities are typically close to half the speed of light, all of our analytical methods break down, and we have to resort to numerical relativity, which solves the Einstein's equations numerically to bridge this gap. So as you can imagine, this is a very hard problem to do, and it took a long while for us to figure out how to do this. Even in 2004, it was considered a big deal to be able to do a single orbit of a binary black hole close to the merger. So that's what this paper is about. It was the first time they could do one orbit close to the merger. And this was in 2004, which is 15 years ago. And then after this, pretty soon after that, we got the first evolution of a binary black hole through merger and ring down. And this was done right here by Franz Pretorius in this paper. And so this essentially solves the binary black hole problem in full numerical relativity, except there's some caveats you still need to figure out, like high spins, high mass ratios, and so on. But this was a big breakthrough. We've come a long way since then. Nowadays, binary black hole simulations can be considered routine. We can do thousands of them in a year. Recently, the SXX collaboration released a catalog of waveforms containing 2018 simulations. And this is a parameter space plot in a reduced part of the parameter space. So here's the ratio of the 2 masses of the black holes, and these are the spin magnitudes. So these are dimensionless spins. So they go from 0 to 1. So there's a decent coverage of the parameter space, and these include systems with precession as well as non-precessing systems. I'll explain what those are in more detail later on, but I just want to show that we have decent coverage of the parameter space. So let me explain how I think of numerical relativity in the context of this project. So we want to solve what we get from a binary black hole system, and what waveforms we get, and what happens at the end of the merger. And to do that, we need to solve Einstein's equations. As I mentioned, this becomes intractable as you get close to merger, so we give the problem to a supercomputer. And at the end of the simulation, what we have is a gravitational waveform that escapes to infinity, and what's left behind, which is a final black hole which has a mass and a spin. So these are the 2 most important outputs of the simulations that are used by LIGO and Virgo. In particular, the gravitational waveform is used to compare with the data and infer the properties of the source of the signal, such as the masses and the spins and so on. And the final black hole properties are used to test general relativity. So as I mentioned, the ring down part is entirely dependent on the frequencies of the quasi-normal mode spectra, which are dependent only on the mass and spin of the final black hole. So being able to predict the final black hole allows us to look for these frequencies in the ring down spectrum and therefore test general relativity. So as I mentioned, Okay, so despite the promise of numerical relativity in predicting all of these outputs, there is one serious limitation, and that is that we have to use a supercomputer. So every time you want to predict the gravitational waveform, you need to do the simulation, which can take a month on a supercomputer, and which takes about 50 cores as well. So it's a very expensive computation. So, however, what we need for LIGO and Virgo is a very cheap evaluation, a very quick evaluation that happens within a fraction of a second. So, to solve the problem, people have used various approximate methods. These are typically called phenomenological waveform models or effective one-body models to bridge the gap between early in spiral and the ring and the merger ring now. So the idea is you start with an ansatz or an approximation motivated by some physics as well as some intuition, and then you leave some free parameters which you will then calibrate to numerical relativity simulations. So here's an example. So this is the orbital phase as predicted by post-Newtonian theory in the Fourier domain. So this is Taylor F2, and you can ignore these terms, but it's just an expansion in the frequency up to whatever order is known in the post-Newtonian expansion. However, the assumption that they make here is that we are missing some extra terms, and we can add those extra terms in with some free parameters, which are these sigmas, and we can try to compare those with numerical relativity simulations and try to figure those out. However, there is a possible flaw in this in that we don't really know that the corrections will take this form. That is just an assumption based on what we've seen before. And so then you can ask the question, is there a way to not do that? Is there a way to not make an assumption and instead directly use the numerical relativity simulations? So that's what surrogate modeling does. We use a purely data-driven approach. We use the numerical relativity simulations directly to build the model, without having to make assumptions about the underlying phenomenology. So the workflow goes like this. Again, you have a binary black hole. So in a recent model, we used 1,500 numerical relativity simulations, each of which took a month, as I mentioned, on a supercomputer. And then from each simulation, we get the same outputs, the final black hole properties and the gravitational waveform. And then the model looks at all of this data and learns how this depends on different parameters of the two black holes. So I'll explain in a little more detail how that works, but it's essentially a learning process for the model. And at the end of it, what you have is a model which can now reproduce these outputs, just like a numerical relativity simulation. So the part that the surrogate model now replaces in this picture is the solving of the Einstein's equations. We don't directly solve them anymore. Instead, the model takes the outputs of the simulations and interpolates between them. So at the end, the model itself is very cheap, so you don't need a supercomputer anymore. You can use a dusty old desktop computer, and you can still get the same predictions. And as I'll show later, these predictions can be made at an accuracy level that is comparable to the original simulations. So in this sense, surrogate models take the numerical relativity simulation outputs, and then they move it from a supercomputer to a desktop computer or a laptop. So a little more concretely, let me give an example of how this process works. So let me start by a very simple example of non-spinning binary black holes. So all the spins are zero, and the only free parameter is the mass ratio. So you can think of this as, so let's say this is the parameter space that we want to model, which in this case is one-dimensional, but I've represented it by this patch because it can have higher dimensions in general models. So, and then in this parameter space of interest, we have a bunch of numerical relativity simulations. So I'm representing them by these markers here, these circular markers. However, because the simulations are very expensive, we only sparsely cover the parameter space, which is what is represented here. What we want is something that can interpolate between all of these and produce a model that is valid over the entire parameter space. So to do this, we first begin by building an accurate basis using the data that we have. So let's say this is what our basis looks like. So these are all the basis functions that we want to figure out. And then they have some coefficients that depend on the parameter. So this basis is constructed using the very waveforms that we have at our disposal, which are the NR waveforms. So you can pick, let's say, these two parameters and orthonormalize those waveforms to build an initial basis. And then you can take all of these different waveforms and you can project it onto that plane that is spanned by these two bases, and you can compute the projection errors for all of these cases. So that gives you an idea of which of these different waveforms is most different from the basis that you already have. In a sense, the one that is more orthogonal to that basis. And then you just add that basis to your existing set and you repeat the procedure until your projection errors are all below a certain level. So you can also think of it in this visual manner. So let's say these waveforms that I draw here are the different, Here in this plot, this axis shows the mass ratio, which is the free parameter, and then this is the time axis. And so let's say these are the waveforms that we pick out to form our basis. So for different mass ratios, the waveform will look different. And then these are the ones that we figured out to be the most different from the waveforms that we already had in our previous set. So this will be our starting basis, or our basis with 4 elements. However, it's much easier to work with slowly varying functions of time. So rather than work with this oscillatory waveform, we could work with the amplitude and the phase of the waveform. So here on the top, I'm showing the amplitude, which is what I'll use as an example in this demonstration. So what we have now is an accurate basis. Let's say four basis points are enough for our example. We have an accurate basis that represents our parameter space such that the projection errors are always below some threshold. So we can write any point in our parameter space as a sum over basis with some coefficients. And these coefficients are currently unknown, but I'll talk about that later on. Okay, so at this point, what we have is we have reduced our parameter space in the parameter space direction to just these small set of waveforms, and we've done that by picking the most important waveforms. So we can do the same in the time direction. We can build an interpolant in time using the most representative time values, such that the interpolation errors are the worst for those particular points until you include them in your interpolation. So this is essentially a very similar kind of picking the most important points procedure. And then at the end of it, what you have is a grid of points. And now all you need to do is fit across parameter space at all of those points. And the reason you want to do that is you have this amplitude as a function of as a sum of the basis elements, but you don't know the basis coefficients. As it turns out, you can relate the basis coefficients at any q to the amplitude values at that mass ratio and whichever particular time value whichever time value you evaluate the fit at. So you can think of it as a matrix inversion problem. You go from the set of amplitudes on these points to the basis coefficients at any mass ratio. So let's say this is the mass ratio that we are interested in. So to evaluate the waveform, all we do is, we first evaluate the fits at each of those points. So that gives us the amplitudes at each of those times. And as I mentioned, we can do a matrix inversion that essentially gives us the basis coefficients at that mass ratio, at that unknown mass ratio. And now we have the basis coefficients and the basis functions, so we just sum them up to get the evaluation of the amplitude at that point. So here in this step, the final evaluation is just summing over time series, so summing over arrays of waveforms. So it's a very cheap evaluation, which is why the surrogate model is so cheap to evaluate. So this is a general picture. I did skip some caveats, but it should give an idea of how we use NR waveforms to interpolate between them and build a model out of it. In particular, the model that I'll talk about deals with precessing binary black holes. So to explain what those are, I have some movies. So in these movies, the black holes are represented by these ellipsoids, and the arrows on the black holes represent the spin of the black holes. And then the arrow in the middle is the orbital angular momentum, which is always perpendicular to this plane. So you can see the orientation of the plane by just following the pink arrow. And then the gravitational wave here is the gravitational wave as seen by an observer at infinity, as from in front of the plane. And this is also the plus polarization only. And similarly, the patches here are the plus polarization of the gravitational wave as seen by an observer that is standing on that plane over there. So whenever the patch is red, it means that the space-time is being stretched. Whenever it's blue, it means that it's being squished. Okay, so the main difference you should see between these two examples here is that the arrows here are always either along the orbital angular momentum or opposite to it. So these are called aligned spin binary black holes, while on the right-hand side they can have generic orientations, and these are called precessing binary black holes. And the reason is that as the binary evolves, the plane of the orbit is always going to be in the xy plane here, while here the spins interact with the orbit, and this causes the orbit to precess around the vertical direction or around the direction of the orbital angular momentum or the total angular momentum. And you can see that in the waveform as well. As the orbit evolves, the precession is imprinted directly on the gravitational waveform. So therefore, this is a very important effect that we can look for in our gravitational wave data and try to infer the precession from that. That will also tell us about the spins of the black hole, which can have very important astrophysical implications, such as how black holes evolve, how they are formed, where they are formed, and how they affect the evolution of galaxies and so on.
Did you say, and I missed it, what the color at the bottom?
That's the plus polarization as seen on the plane here. So red is positive, blue is negative.
For the radiated gravitational,
Right.
which are evaluated following.
Right. So it's an approximation that I'm using it close enough, but it is the farther away I place the plane, the better that approximation would be. But this is just for an idea, I guess. Okay. So therefore, it's very important to be able to predict the precession given a set of black holes in a binary. So that's what this model is about. And to explain why the name precession is used, you can think of it as analogous to a precessing top. So here, this is a top whose spin axis is tilted with respect to the vertical. So as it evolves, the spin direction precesses about the vertical direction. So in a very similar manner, the orbital angular momentum as well as the spin directions will precess about the total angular momentum direction. So that's why we use the name precession. Sure.
So on the left, we're talking about an external.
Sure. Right.
On the right, there's no external.
Right. I mean, it's an approximate analogy, I guess. And
Fair enough.
yeah.
Is there more insight you can give on that, or it's an approximate analogy?
No, I mean, here it wouldn't precess if there's no gravity. So, right. So I don't think. Okay, so therefore we want to model this vast 7-dimensional space of precessing binary black holes. So the first model that was able to do this is called NR Sur 7D-Q2. Here 7D is the 7 dimensions, which was built by Jonathan Blackburn, a grad student here a few years ago. And the current model I'll talk about is an extension of this to more general mass ratios, where so mass ratio here is the ratio of the two masses. So we go to more unequal masses where the black holes can have mass ratios up to 4. So to cover this 7-dimensional parameter space, we use 1528 numerical relativity simulations. So that's shown in this plot here, which I won't go into the details of, but each index here is a different component of the spin or the mass ratio. So we have decent coverage in the full 7-dimensional space, but even with 1528 waveforms, it's still, I think, about 2.9 or 2.7 or 2.8 points per dimension. So it's a very sparsely covered 7-dimensional space, but with a lot of simulations.
Could you tell us what the 7 dimensions are?
So these are the mass ratio and then 2 spin vectors, which each have 3 dimensions.
Right, okay.
So So that's a full 7-dimensional space for non-eccentric binary black holes.
So chi is the...
So this would be the magnitude of the spin. Chi, yes. And then these are the angles with respect to the vertical at some frequency. So this covers the full spin space, and this is the mass ratio.
So can I ask about that? So one assumes that the magnitudes don't change much over the evolutionary time.
That's right, yeah.
And of course the phi azimuth angles are whizzing about. Do the polar angles change much over time?
Yeah, they do change. Not as much as, I mean, it's hard to put a constraint on how much they change, but they do visibly change as well. But not as much as phi, of course.
In such a way as to keep the angle of the total spin. That's one plus S2 with respect to the orbital angular momentum more or less constant.
More or less, yeah. Yes, that's true.
Modulo gravitational waves.
Yes, that's right. I mean, in general, the total angular momentum direction is the one that you can really approximate as being constant. But the spin direction is also more or less constant, but not as constant as total angular momentum.
Are these spin parameters defined as some reference frequency?
Right. So all of our NR waveforms are 4300 m before the merger long, so they're all defined at the start. But we can define them at a different frequency depending on the model. Okay, so this new model then covers all of these simulations, and in particular, the gravitational wave on the sphere can be decomposed into a set of spin-weighted spherical harmonic modes, and typically the L equal to 2, M equal to 2 mode, which is called the quadrupole mode, is the dominant part of the sum, and most models model only the dominant quadrupole modes, but we also model all the higher order modes up to L equal to 4. And in addition, we model the spin and precession frame dynamics, so we can predict how the spin and the plane of the orbit evolves as the binary evolves, and these are all internally used in the model. Okay, so as I mentioned during the demo, it's much easier to build a model for a slowly varying function of time. So we start with something that looks like this, which has a lot of modulations, and we want to simplify that in order to build a surrogate model for it. So to do that, we first do a frame transformation where we go into a frame that tracks the precession of the binary. So on the left here is it's the binary in the inertial frame, and on the right is the binary in the co-precessing frame, in which the z direction is always along this pink arrow, as you can see. And this essentially takes out most of the modulations due to the precession and moves them into the frame transformations rather than the waveform. And now you can see that the waveform is much simpler. It doesn't have these modulations, and you can actually approximate this as being an aligned spin binary black hole. So this is a big simplification where all of the modulations, or most of the modulations, are separated into the frame transformations. So in fact, we do a little more than that. So this is the waveform in the inertial frame. So the orange curve here is the 2-2 mode, and the blue is the 2-1 mode. And then once you go into the co-precessing frame, this is what the two modes look like, which now is much simpler, and you don't see significant modulations in the 2-1 anymore. And the other important thing to notice is that the 2-1 mode in the inertial frame can be comparable to the 2-2 mode at times, which is not what you expect for an aligned spin binary black hole. And the main reason this happens is when the plane of the orbit precesses, all the L equal to 2 modes mix among each other, and then the 2-2 mode, the power of the 2-2 mode can go into the 2-1 mode as well. But by cancelling that precession, we recover the hierarchy of the modes, where the 2-2 is now much larger than the 2-1. And we can simplify this even further. But so far, we've done a transformation where the z direction is in the plane of the orbit. We can do a further transformation by rotating about that z direction, and we can rotate by the exact amount that is equal to the orbital phase of the binary. So that in this frame, the binary is just getting closer and closer without really rotating. And if you do that, then the waveform looks even more simpler, and this is called the co-orbital frame because it orbits with the binary. And it essentially looks like a non-oscillatory function now. there are still these oscillations here, which are the orbital time scale oscillations due to precession. These are called nutations. And we can simplify the picture even further if we look at the 2-2 and the 2-2 combinations of modes. So if you look at them, if you look closely here, they'll have opposite signs for these modulations. So we can use plus and minus combinations of these two lines here to get this line, which is a plus combination, which essentially removes all the modulations that we see, and then the minus combination, which has all the modulations but is much weaker, and we don't need to model that as accurately. As long as we model the dominant part more accurately, our overall accuracy will improve. So we went from this very complicated picture to building a model for these simpler pieces. Yes?
Is that last simplification rigorous analytical?
Rigorous
And can be shown analytically? Or
so it's done.
Say, I can do this.
I mean, we use the NR waveform itself, and we use everything from the waveform, not from the orbital dynamics and so on. So we compute the orbital phase from the waveform here, and then do that, and do that. And then this combination is also, I think there can be some analytical motivation for this. I'm not sure if it's mathematically shown anywhere, but this is true in PN as well. And
I mean, the reason why I'm asking is that sometimes, you look at a bunch of examples and you say, oh, this looks like it works.
oh,
Then when you get to Q equals 92, it doesn't work, and you didn't know that.
no, I think there's
Analytically rigorous.
a geometric motivation for that, where the 2-2 and the 2-2 are the north and the south pole dominant terms, and then they have these modulations. I think you can maybe relate them, even though not exactly, which is why this is not exactly. This grows near the merger here, so that's like some approximations there.
The plus and the minus combinations are just measures of the reflection symmetric and reflection antisymmetric parts of the wave. Right? The part that's symmetric across the orbital plane and antisymmetric across the orbital plane.
Right. So I guess that's why there is, for precessing systems, there's no real plane of symmetry, which is why you always have this minus piece.
So the symmetric part, you would expect to see no orbital wiggles, and we don't. Is that what you're saying?
Oh, and as for why there are no wiggles?
Yeah, that was my question. Why do we see no orbital wiggles in the plus combination? Is that rigorous? Is that analytical? That was my question.
So it's rigorous in all the simulations that we looked at.
With the oracles, it's rigorous.
Yes.
Okay. Until you get to Q equals 93, it spins at 0.9.
Yes. Well, we have spins 0.999, 998.
You have 6 nines?
No, 3, 2. 2? Yeah. Roughly 3, but not precessing. Okay, so we simplify the picture by doing all of these transformations, and we build a separate surrogate model for the frame transformations so that we can go back from this data to the original waveform. And both of these data pieces that we build a model for are very slowly varying functions of time. This is not that slowly varying, but it's very subdominant. So, and then we take the example of the demo that I showed before, and then we build a surrogate model for each of these different pieces in a very similar manner to the demo. So at the end, what we have is a full model for the precessing binary black hole, and I won't go into more details of the methods, except I'll just skip to the results. So we want to measure how well this model is doing, and to do that we use something called the mismatch, which is an inner product between any two waveforms. It's defined here, but you can just think of it as the lower the mismatch, the closer two waveforms are to each other. So to measure the accuracy of our model, we compared the model with the numerical relativity simulations. And then this is the error histogram for our model, the red histogram. And
this includes all LM modes.
All the ones up to L equal to 4. And in the NR data, we include up to 5 so that we get an error measure of neglecting the higher modes. And that's included in this error measure.
Would you get similarly kinds of agreement if you just included the Y225?
Yeah, more or less the same. Okay, so that's the error measure for our model, and we want to compare it with numerical relativity error measures. And the way we do that is we do multiple resolutions of the same simulation so that we can measure the error in the simulation. And then this histogram is the mismatch between the two highest resolutions that we have. And as you can see, the surrogate errors are well within the numerical relativity error estimate. And this essentially shows that the model is capturing all the physics that is present in the simulations, and it is capturing all the precession effects at the same level of accuracy as doing a full numerical relativity simulation. And you can now compare this with existing models such as SEO-BNR v3, which doesn't model directly against precessing numerical relativity simulations. So that's one of the main limitations of this model, and that shows up in the error measures as well, where the errors are about at least an order of magnitude larger than the errors for the surrogate. Yes.
So the numerical relativity waveforms have numerical norms.
Right.
And they have jump radiation.
Right.
The surrogate waveforms don't have.
Well, so even before when computing these measures, we always truncate the junk radiation. Even before we build the surrogate, as well as when computing these mismatches, the junk radiation is thrown away so that it doesn't affect these things. Okay, so the surrogate is essentially doing as well as numerical relativity. To get a concrete idea of one particular case, this is the worst case among all the 1528 numerical relativity simulations. So the top is the worst case for the surrogate model. So the black curve here is the NR data, and then the red dashed is the surrogate model. And even at its worst case, it does reasonably well and follows the NR data reasonably closely, which is what we saw in the previous plot. And and by comparison, the EOB model is noticeably different, and this is reflected in the mismatch plot. And similarly, the bottom plot is the worst case for the EOB model, where it's a much larger difference, and the surrogate here happens to do much better. So all of this is reflected in the mismatch plots, but this is just a concrete example. So now you can ask, what do we need to do to be ready for the next generation of gravitational wave detectors? Which models should we use, and so on? So you can take the errors that I just showed you, and you can compute the SNR at which these errors will become significant. So there's some approximate ways to do that. According to this paper, your mismatch needs to be always less than 1 over 2 times the SNR squared. There are different measures, but this is the one that I picked as my measure. And then, so this is the signal to noise ratio at which these two models will become noticeably different from NR in our gravitational wave detections. So if we treat NR as the true waveform, this would be when we are getting when our modeling errors will become larger than the statistical errors. So, and then you can see that again, this is about an order of magnitude or so difference. So you can look at GW150914 when it was detected, and this is the SNR about 24. And you can see what happens to that SNR with increased sensitivity. So at design sensitivity, it will be about 3 times as sensitive, which will be roughly 2022. And even by that time, this current EOB model, all of its errors will now be, for anywhere in the parameter space, its errors will be much higher than the statistical errors. So we need to be worried about that. And in contrast, the surrogate model is safe until about 2020 something, 2030, let's say. By 2035, we'll have the next generation of gravitational wave detectors, which will be a factor of 10 improvement over design. And so that is when the surrogate will start having trouble. And you can see that the surrogate will be kind of at the same stage in 2035 as what the current models are right now. So for at least 15 years, we should be fine with this model.
So you ignore calibration.
Right, and assuming we'll figure out how to do improved calibration in the future.
Right, but just to set the scale, so if calibration currently is allowing to detect design only 2 or 3%, where does that lie? And if we can aim for 1% or better, where does that lie?
So I think so 1%, that's in the amplitude or the phase, right? It's not the mismatch kind of error.
Amplitude, 5
Okay, so I think, if we assume that's about mismatch of 10 to minus 3, so that we're not currently worried about it. Otherwise, we would be currently worried about it.
Oh, we're currently worried about it.
Okay, okay, so let's say 10 to minus 2. So then that I think would be somewhere in between here.
Yeah.
Okay, so in essence, surrogate models can be the modeling method for the future and can solve the modeling method for the high precision gravitational wave astronomy era. So you can say, okay, so at this point, what next? The model is kind of not working anymore. Well, the answer is simple. The surrogate models are essentially limited by the numerical relativity resolution, so you just need to make new ones with more accuracy. So you just go to Mark and tell him to do new simulations. Okay. So far I've talked about the gravitational waveform. So, however, as I mentioned, there's two important outputs from these simulations, and I've only talked about this one so far. So let me talk about a surrogate model for the final black hole quickly. So you can think of this whole process as a nice Feynman diagram. So you can start with the two black holes that you have. Each of them has a mass and a spin, and then they get closer, and then there's this fuzzy interaction region, which is the domain of numerical relativity. So I'll just ignore that for now. And at the end of that, what you have is the gravitational waveforms that escape to infinity, and then the final black hole properties. So these are these properties, in fact, have very nice physical meaning. You can think of the final mass as it's related to the conservation of energy, where you can take the total energy that you start with and you subtract the energy lost to gravitational waves. What you have is the final mass. Similarly, for the final spin, it's related to conservation of angular momentum. And then the final black hole can also have a velocity, which is called the kick velocity. So this happens because the gravitational radiation can be anisotropic as the binary evolves, which means that the center of mass of the binary will get a recoil in the opposite direction. And a lot of this happens near the merger, where the anisotropic part is strongest. And so the final black hole can have a recoil velocity, which we call the kick. And this kick is similarly related to the conservation of linear momentum. You take the total momentum you started with and remove the momentum lost to gravitational waves, you get the final kick. So these are all very well-defined final quantities. And the idea here is to build a map from the initial quantities to the final quantities and then skip the entire merger process. And the reason we want to do this is for tests of general relativity. So as I mentioned, the final ring down part of the signal is the frequencies in that signal are entirely dependent on the mass and spin of the final black hole. So being able to predict the mass and spin very accurately lets us look for those frequencies in the data and test general relativity to a higher precision. So here's an example use case of this model. So here is the final mass and spin measurement from the first gravitational wave event. You can ignore these two curves here and just focus on the yellow curve. So that's the mass and spin as inferred by using a linear quasi-normal mode model for the ring down. And you get a reasonable measurement using only the ring down spectrum. Similarly, you can use the full waveform. You can take the full waveform posterior samples that you get in your data analysis. So that gives you the mass ratio and spins of the binary, and then you can use a map like I talked about to go from the initial parameters to the final parameters, and that gives you a different value for the mass and spin. And if GR is consistent, we should find that the two methods of measuring the mass and spin are consistent with each other. So this is a test of general relativity using the map as well as the quasi-normal mode spectrum of the binary black hole. So therefore, this was recognized as an important problem ever since the first numerical relativity simulation. And however, the approach has, over the last 15 years, the approach has always been a phenomenological approach where you come up with an ansatz or an approximation for what your final mass should be like, and then you have some free parameters. So here all the k terms here are free parameters, and m's and delta m's and spins are all combination of masses and spins. So all the k's here are free parameters that are fit to the data. So this is a three-dimensional fit where they ignore precession. So, however, even for the three-dimensional case, you can see that the problem looks pretty messy, and it's not clear which of these terms is well motivated, which of them are the most important, and or how you come up with those. So, can we do something different? And the answer is yes. We can use the surrogate modeling philosophy and for the same problem, and we use Gaussian process regression, which is used in some machine learning kind of applications. And the nice thing is that you don't need to assume a phenomenology. Instead, you let the data speak for itself, and then the model will implicitly figure out the phenomenology for you. And again, we train directly with precessing numerical relativity simulations, and I'll show in the next slide or so that we can reproduce NR as accurately as NR itself. Okay, it's the next slide. So this is again an error measure for the final mass surrogate model. So the red histogram again is the error for the surrogate model, and then the black histogram is the error for the NR, the estimated error in the NR simulations. Again, you can see that the surrogate is very good in reproducing numerical relativity simulations. And then all of these dashed histograms are various existing models which don't fully capture the effects of precession, and therefore they have about an order of magnitude larger errors. And these different models are listed here if you want to look them up. And similarly, we have a model for the final spin, and the story is very similar. The surrogate is very good. Other models are not that good. And then this is the first model that accurately predicts the full three-dimensional spin of the final black hole. So that means that we can predict both the direction as well as the magnitude of the spin, and even in that case, the surrogate is well within the NR errors. So this is the error in the direction of the final spin. And right, why that's so less? Why the surrogate errors are so less, or no?
Yeah, I mean, right. How can it be better?
Yes. So I mean, here this error estimate is actually an overestimate. So the resolution error doesn't always turn out to be very good, and we actually have some good reasons here for why that's happening. It's because the junk radiation happens to be affecting different resolutions in different ways. So the high resolution simulation is fine, data set is fine, and we can build a model using that. But if you want to compare the low resolution simulation for the same parameters, turns out that the spins got tilted a little bit extra, and it's a different physical system. So it's a very conservative error measure.
The circuit doesn't have that problem.
Right, because it.
Since the circuit is more accurate than the numerical relativity that it's based on.
That's true, in the sense that we're not limited by the junk radiation. Okay, so similarly for the kick velocity, the story is very similar. Surrogate is great. And in interest of time, I'll just skip to the final few plots. So again, you can ask, when do we really care about these kind of more improved models? So you can take the example of GW150914 again, and you can look at the errors in measuring these final mass and spin quantities with that detection. So these are right now dominated by the noise of the detector, so these are statistical errors. But as the detector improves, we expect that these errors will go down. We can roughly estimate them as going as inversely proportional to the SNR. And so at design, it'll be about 3 times the SNR of O1. So then these errors will go down to 3 times 10 to the minus 2 level. And then you can take the errors in my previous plots, and you can find the 95 percentile values for the existing fits, and you can compare these two values. So this is now a systematic error for these models. And you can see that the error in the mass is still pretty good. But the error in the final spin is very close to the limit put by the statistical error. And this, I think, is a little worrying because we can potentially make revolutionary claims about tests of general relativity using these models. So we want our model errors to be well within the statistical errors of our detectors. So about 5 times the SNR of the first event, they'll become equal, and then we won't be able to use them anymore. So in comparison, our fits are about an order of magnitude better. So that means that until 50 times the SNR of the first event, they should be fine, which again is about 3G, which is 15 years from now. Okay, so to end with, I'll show some more movies. So what I didn't mention about these movies is that they're based entirely on surrogate models. So until now, if you wanted to make a movie of a binary black hole, you'd have to buy a supercomputer and run a simulation for a month and then render the simulation. But now, since surrogate models can reproduce them very accurately and very cheaply, you can use our Python package to install it within a few minutes on your computer and then run this visualization within 5 seconds. And it doesn't use numerical relativity data directly, so it's very fast. And also it's very accurate because it relies on surrogate models. So in this visualization, this is a visualization of a phenomenon called superkick, where as the black holes get very close to each other, you'll see that the two spins of the black holes get aligned in the same plane, which should happen very soon. And this is a particularly special configuration where the final kick will be very large because of that alignment. So this, if you see, they're in the same plane, and the two spins are opposite each other but with an angle. So this is called the superkick configuration. And if I let the movie go on, you'll see that after the merger, the final black hole will fly away with a very high velocity. But to make that clear, I'll speed up the movie right now. There you go. So the final velocity here is about 100 the speed of light, so that's a very high velocity. And this can have important astrophysical implications because if we have a system like that, it will get ejected from almost any known galaxy, including the most massive elliptic galaxies. So that means that using the kick measurements, we can constrain the retention rate of binary black holes, and that lets us know whether these binary black holes remain in their galaxies or they get ejected out and are then free, and which can again impact the evolution of galaxies. Okay, so to summarize, numerical relativity simulations are very accurate, but they're also very expensive. So surrogate models come to the rescue, and they can cheaply reproduce the accuracy of these simulations. I talked about surrogate models for the waveform as well as the final black hole properties for generically precessing binary black holes. And these models are currently the most accurate models for precessing binary black holes within their parameter space range. And they improve existing models by an order of magnitude. So in that sense, surrogate models take binary black hole simulations from supercomputers to your laptop. And as a finishing note, all the movies that I talked about can be installed and you can run them on your own. You go by going to the website here, and apparently you can point your camera at that, and without the need for an ad, it should be able to pick it up because cameras are smart nowadays. And so I'll end with that. Thank you.